Okay, let us move forward with the theory of the integral calculus. So I open this important chapter that is called the theory of integration. According to Riemann. This can sound strange because one said, okay, the integration is a mathematical fact. You don't have to invoke names. But the truth is that there are several theories of integrations. And from the pedagogical point of view, the most elementary one is the one due to Riemann. Okay, it is elementary, but it is not so easy. And another theory, and probably you will not meet, at least in engineering studies, another theory is the theory due to Henri Lebesgue. So, there is 1 century from Riemann to Lebesgue. Lebesgue worked in the first half of the 20th century. And the theory by Lebesgue is the most powerful theory of integration that we have. And then there are other generalization, Lebesgue-Stieltjes, or Bochner integral, and so on and so on. But the basis of contemporary theory of integration is the theory by Lebesgue. But it is considered as too difficult to introduce it immediately. I don't fully agree with this point of view. But however, I will remain to Riemann. You will see that you have a lot to learn also by Riemann integration. So, as I told you before, we want to solve the problem of the areas, and this is the problem of the areas. Compute the area. For this year, it is just this. Compute the area that stays below a graph, so between the graph of the function you are studying and the x-axis, and the area will have a sign. So let us go with rigorous setting and definition. So we start from an interval AB, and in particular we have a finite A and a finite B. Okay, B is larger than A, and then we have a function from the interval, the closed interval AB to R. And this function has to be bounded. At first, we just require that f is bounded. Okay? For the moment, no continuity, no other hypotheses are verified. So you have that the supremum of f, when x is in AB, is finite, and the infimum is finite too. Okay, this is the only thing that I require, that at the very beginning. Okay, and the problem that we want to study is the following. Is compute the area between the graph of f and the x-axis. Okay, this is the problem. And notice that I'm talking about the area between the graph and the x-axis, but we don't have a rigorous notion of that. We just have an intuitive notion. What is the area? The area, so roughly speaking, if this is a wall, and you want to paint it, you want to paint it just this region, You want to know how much paint do you have to use. So it is not really a mathematical terminology that I use, just an intuition. Okay, we define the area for polygons, for squared, and so on and so on. You can say the area is the number of unitary squares that can be put inside the region. But this is again is intuitive because since the region you want to study is not regular, in particular it is curved, then talking of number of squares that are contained there is not proper because there is no such number, very simply. So what I just want to stress is a sort of a subtle thing, but what we will do through the theory of integration is not really to compute the area, but rather to define the area. What is the area there? Okay? Don't be afraid and don't worry if you don't catch this nuance, okay? But if you catch it, it is better. It is not important for what follows. But what we will do through the theory of integration is define the area. Okay, let me again take this picture from here and copy it here. Good. And so first let me start. How would you do? And the first idea is to proceed like that. So let me introduce this definition. So a finite set of points in the interval AB and we will use this notation, sort of capital P will be equal always to, the first point is A, and we change its name, and we call it x naught for notational purposes, and then there will be another point x1, then x2, and so on up to xn equal to b. So this finite set of points is called a partition of the interval AB. So let me draw it properly here. Here, for instance, we can also consider another branch here. And so here we have the point A. Here we have the point B. Here, and then we introduce some intermediate point here, x1, here x2, x3, x4, for instance, then many dots, and here we have b equal to xn. Okay, this is a partition. And then you will use also a notation. We say that delta xj will be xj minus xj minus 1, and j will range between 1 and n. So delta xj is the size of the jth interval of the partition. For instance, here we go here. we consider this distance between x2 and x3, and this will be delta x3. Okay. Now, after introducing that, we also introduce other notations. For instance, here, mj, little mj, will be the infimum of the function f of x when x is in the jth interval, so in xj minus 1, xj, closed. On the other hand, capital Mj is the supremum of f of x when x is in xj minus 1, xj. Okay, so again, consider this interval, the third interval in the partition of the picture here. So here you have x2, here you have x3, and of course, here this height is the infimum in this interval, so this will be m3, and the supremum in this interval is here, and this will be capital M3, okay? Of course, this small m and capital M are defined for every interval of the partition. And now, other notation, but also it is quite important, so I give it the name of a definition. And I say the following. I said that the quantity small s of the function p and of the function f related to the partition p. Okay, so it is a quantity that depends on the function we are studying and on the partition we took. So this is equal to the sum for j going from 1 to n of small mj delta x j. Okay? Okay, this is called so let me be precise, even though a bit pedantic, lower sum of the function f with respect to the partition P. Okay, let me give you a remark. What is this lower sum? I just write you here as FP. Okay, here I used the sigma symbol. Now I think you should be well acquainted with this symbol, but however, let me be perhaps more elementary and clearer. So this is M1 delta x1 plus M2 delta x2 plus mn delta xn. And remember, what is this this quantity? First we have the infimum of f of x for x in the interval x0 x1 times delta x1, which is x1 minus x0, plus the infimum of f of x for x in the subsequent interval x1 x2 times x2 minus x1, so the size of the same interval, plus dots, plus the infimum of f of x with x in xn minus 1 xn, and here you have xn minus 1. So, and try to picture what are these quantities. Let us start with this. The infimum of f of x in the first interval dot the size of the first interval. Let us go to the picture. So, the first interval is this one, x0, x1. And the infimum in this interval is, roughly speaking, here. So, here you have m1. And so, you have m1 times the size of this interval. This can be represented as the area of a rectangle whose basis is here, whose basis is x0, x1, and whose height is m1. So the first term of this so-called lower sum, small s fp, is this quantity here. I'm not able to do it properly, I don't know why. Let me try here. Is this one. This is the area. It is the area of the first rectangle. Okay? So, area of the first rectangle in the left-hand side of the picture. Okay, so with basis is the interval x naught, x1, and the height is m1, small m1, okay? This is true for what concerns this term. From the second term, it is pretty analogous, because here we go to the second rectangle, and here we have m2, the height, here we have the basis, and again we have this rectangle. And for the third, here we have m3, and this is the third term in the lower sum. For the fourth, again the infimum here is, if I picture it in a proper way, okay, and this is, okay, let me consider here n equal to 5, so I can end up with this picture, and the infimum is here, this is m5, and so we have this area for the last rectangle. Okay. So the lower sum is equal to the sum of the areas of the green rectangles. But be careful with sign, in the sense that the last rectangle, this guy here, will give a negative contribution to the total area. Will give a negative contribution because m5 here is negative. The height is negative, so the basis is positive, the height is negative, so it is a negative contribution. And now, notice this fact. So when we compute this lower sum, what is the relationship with the area we want to compute? That is the area between the function and the x-axis. So for the positive part, for the positive contribution, you know that the positive contributions are inside the curve, so inside the area that we want to compute. So for the positive contribution, we will get an area that is less, or at least not larger, than the area we want to compute. For the negative contribution, notice that here we have a contribution that is in some sense more negative than the one of the negative part of the area we want to compute, so it is less. But there is also a positive part. So this is positive. The corresponding area of the rectangles is negative, so we end up by saying that the contribution of this negative rectangle is much less than the contribution of this part of the area. Okay? So we can conclude that by direct comparison, irrespective of the partition we chose, the lower sum is not larger than A. A is the area we aim at computing or defining. So in other words, there is another beautiful song by Frank Sinatra. In other words, it was, what is the title of this song? So homework, find this very beautiful song by Frank Sinatra that at some point says, in other words, I love you. In other words, every lower sum, Fly Me to the Moon. Fly Me to the Moon is the song, very beautiful, so listen to it. In other words, every lower sum is a lower bound for the area we're interested in. Okay. And so now, so we got a lower bound, and now in a completely analogous way, by exploiting the capital M, we will get an upper sum. So an upper sum is the following, and let me copy the definition of lower sum and modify it. So the quantity, this time we use capital S, Fp, is equal to capital Mj, delta Xj, and this is called the upper sum. Of the function f with respect to the partition P. And again, we have a remark. And the remark is that S, capital S, Fp, will be what? First term is the supremum of f of x in the first interval x in x0, x1, times x1 minus x0. Plus dots, 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 and the supremum of f of x for x ranging in the last interval xn minus 1 xn times xn minus 1. And so what we get at the end, let me construct it again. We choose another color. This purple can be a very beautiful color for that. So in the first interval, the supremum is this. This coincides with little m2, but this is also capital M1. Oh, no, this purple has been already used, so. Brown. This is capital M1, and I have to restore this small m2. Okay, capital M1. And you see the first contribution of the upper sum is this brown rectangle that contains both the green rectangle, which is the corresponding term in the lower sum, and also the part of the function, of the area, with the same basis that stays below the graph, okay? And this is the same, then you repeat the same construction for every interval. Here I will go a bit faster. Here you have M2, capital M2, and again and again. Here we have capital M3. For capital M4 we are here. Okay, lines are not so pretty straight, but don't be impressed by that. And also here I will superpose some writing, but don't be very impressed. Now you are used to my inability of doing good drawings and so on and so on, so do it by yourself. And again, like before, we say that the upper sum in this picture is the sum of the areas of the brown rectangles. And again with sign, the picture they are all positive. So and in a completely analogous way with respect to what we did with lower sum, we see that the upper sum is larger than the area we want to compute. Because for completely positive region, the area we want to compute below the graph is included, is strictly contained in the area of the brown rectangles. Okay? For a non-completely positive region, for what concerns the positive part, then the area is larger, and for what concerns the negative part, it is much larger, because here, the area we're interested in is negative, but the area we are computing with the upper sum is positive, so it is much larger than that, okay? Again, by direct comparison, we have that the area we want to compute at the end will be less than the upper sum, larger than the lower sum, and this is true irrespective of the partition. So we were able to construct quite easily, quite naturally, a lower bound for the quantity we want to get and an upper bound. And now probably you can just have an intuition of what will be the game of the theory of integration. The game will be the following: to make this lower sum larger and larger, this upper sum smaller and smaller, in such a way there will be only one possible value trapped here. This is the game. To be very efficient and find very good lower sums or very good upper sum in such a way that there will be only one value here. This is really powerful. Okay, go to the picture and see it. This will mean to be able to find a partition of the interval so good in such a way that the upper sum will be, the lower sums will be closer and closer to the area we want to compute, and also the upper sums. And it is intuitive what you want to do now, what you have to do. You have to make this interval thinner and thinner. If you do that, then you have the chance to find a lower sum and an upper sum that are very close together in such a way that at the end, only one value will be trapped here. So this is the game. The game. So, the purpose. Find a lower sum and an upper sum that are so good that, okay, only one possible value for A can satisfy the double inequality Let me give you this asterisk. Okay? So only one possible value can be trapped here. At this point, we will be forced to say this is the area we want. But notice that there is a conceptual problem. The problem is that so it seems that in order to do that, one has to choose thinner and thinner partitions. Or partition with finer and finer intervals. But this seems to be a sort of an infinite recursion. Because you make it thinner and then it is not good enough and then you make it thinner and so on. But this seems to give rise to an infinite process. So the question here now is how to stop this infinite process of making thinner and thinner partition. Through the analysis. This would be mathematical analysis stuff. Gives such a tool. Okay? And we will see